Hello, and welcome to our webinar. This goes out to our customers, students, interested engineers, and last but not least, to our competition. My name is Emilio Meza, and I am your moderator for today's webinar about humidity, part of the Power Module Reliability Series. So high humidity environments presents a relatively common but not well understood problem for power electronics. Properly addressing seemingly random humidity-induced failures requires an understanding both of the environment around a power semiconductor module, as well as the high-risk operating conditions. Before we get started with the presentation, some words about our webinar platform. In case of connection issues to the presentation stream or the sound, please try refreshing your browser window. In your browser, on the right-hand side, you see the chat window, which you can actually hide to increase the presentation window. In case you have any comments or difficulties, please let us know via the chat. All messages are private and only we can see them. If you have any questions about the content, please mark them as a question. We will try to answer your questions at the end of the presentation. Any questions that we are not able to answer today will be answered in the coming days via email. You can also send an email to webinar@semikron.com at any time, and we will get back to you as soon as we can. Finally, we will also share the slides as a PDF file at the end of the presentation. You can find this handout in the Apps menu with the three dots in the lower right corner of your browser. Your presenter today is Paul Drexage. Paul graduated from the Rochester Institute of Technology with a bachelor's degree in electrical engineering. He then worked as a design engineer in Semikron's Solutions Group, designing power electronic subassemblies. Paul now serves as the applications manager, and his team is responsible for troubleshooting existing designs and addressing new customer designs. Enjoy the webinar. Paul, the floor is yours.
Thank you, Emilio. This webinar gives an introduction to the concept of humidity as it pertains to power electronic systems. We're going to start with some definitions and then discuss how humidity affects the power semiconductor modules. And then we'll discuss what causes this high humidity in power electronic systems and what we can do to reduce the negative effects. An introduction. So what we have here is a power semiconductor module, exaggerated in scale, which is mounted inside a piece of electrical equipment, perhaps a motor drive or solar inverter. Depending on the application, that electrical equipment enclosure might be rated for outdoor use. So we show this building here as optional. And so we usually speak about one environment with a given set of temperature, moisture, wind, pollution, etc. But for the purposes of this discussion, it's really important to differentiate between the larger macro environment outside, shown here as one, and the different micro environments that can occur around and inside a power semiconductor module. The effect of this outside environment is usually dominant. So it's expected that if you're in a tropical region where there's a passing thunderstorm, it will yield high humidity within the electrical equipment or power module. What's less apparent is how this electrical operation of the power semiconductor module influences the environment immediately around it. As we will discuss, the heating and cooling of this power semiconductor module can actually generate high humidity conditions immediately in the microenvironment in and around the module, even if the conditions in the building or outside seem relatively dry to a human observer. The word humidity specifically refers to water as a vapor that is diffused into air. We can have water vapor without heating water to its boiling point, as in the case of standing water evaporating. Now, there are a number of ways to measure humidity, but for this discussion and for the available standards and measurement methods that we all have access to, we'll talk about two types here. So absolute humidity is the mass of water vapor in a volume of air. Many of the charts and standards available to us use this value as a constant, and it has some value showing the relationship between temperature and relative humidity. Relative humidity, which is what we'll use for all of our discussions, is a ratio of the pressure of the water vapor in the air to what's called the saturation vapor pressure. This saturation vapor pressure is essentially how much water vapor the air could potentially hold at a given temperature. As we'll see in a moment, it also turns out that relative humidity happens to be easy to measure. So this graphic on the right is a generic version of what's known as the IEC, the International Electrotechnical Commission, climatogram. And it illustrates where we want to keep our microenvironment in and around a power semiconductor module. We have relative humidity on the y-axis here, temperature on the x-axis, and it's obvious, I think, to most people that going too hot or too cold will cause issues in a system. But what might be new to you here is to see that for these fixed absolute humidity lines here, which are these blue lines, we can see that a decrease in temperature will result in an increase in relative humidity. And if we increase that relative humidity too far, we're going to have condensation. So we want to differentiate between that word humidity, which is water in vapor form, and condensation, which is water in liquid form. This is important because in a few slides, we will discuss how you can have failures of power electronics in high humidity environments without obvious condensation. But nevertheless, condensation is a risk anytime you have an object that drops below the dew point for a given environment. The most relatable example is a bottle of cold liquid taken from a refrigerator and put out into a room where you have beads of water, which are condensation, forming on the sides of that bottle. And what's happening here is that in this room, we have a given humidity and temperature. For example, 60% relative humidity and 20 degrees Celsius air temperature. And so this graph here shows us the dew point for that given condition. So if we look at the intersection of that 20 degrees Celsius room temperature and the 60% relative humidity line, we can see that the dew point over here is 12 degrees Celsius. So what that means is that any object in the environment that is 12 degrees Celsius or lower will have condensation form on it. So the bottle of liquid that you take out from the refrigerator and put into that 20 degrees C room might be 10 degrees Celsius, and you'll have water condense from the surrounding air onto the bottle. But conversely, if you had only left that bottle in the refrigerator for a short time and it had only cooled to maybe 15 degrees Celsius, no condensation would form. Presently, there's no commonly accepted international standard defining the microenvironment around the power semiconductor module. The best we have is something like IEC 60721 series of standards that classify the external macro environmental conditions that a finished product will be subjected to in operation. And so what we're showing here is a recreation of that climatogram from IEC 60721-3-3, which classifies environments for equipment in a stationary weatherproof location. Different environments are then defined by different climactic classes, one of which is plotted here in red. For example, if a power converter can withstand a 3K22 climactic class, you can see here that it is designed to operate in a relative humidity from 5% up to 85% relative humidity, and from temperatures from 5 degrees Celsius up to 40 degrees Celsius. And so that would mean that whatever electrical enclosure you're putting around that electronics needs to be designed such that all of the electronics inside can survive if the external environment falls within this red boundary. And so climactic class 3K22 is actually a relatively benign environment, as this class also states that condensation and wind-driven precipitation are not allowed, which you might see in an indoor industrial environment. There are other climactic classes where condensation is allowed, in which case the electrical enclosure would have to be designed such that the condensation did not affect the electronics inside it. Lastly, since most electrical components are designed for a larger temperature range than this 5 to 40 degrees Celsius that you see here, we can extend that to a more common negative 40 degrees to plus 85 degrees temperature window, while we're still adhering to these limits for absolute humidity to get this blue curve shown here. And this is used with more integrated power electronics assemblies, such as the intelligent power module, like the SKIP product that we have, which is intended to be installed in a location defined as a 3K22 climactic class with a quote unquote extended temperature range. Now, this IEC climatogram can also be used to illustrate how relative humidity changes with temperature. And we'll look at the transition between three states in a hypothetical environment. And to simplify this example, I'm going to have to make some assumptions here, namely that we have a permeable parcel of air with a fixed absolute humidity. So we have a fixed amount of water molecules and a fixed volume. We've arbitrarily chosen 13 grams per cubic meter of absolute humidity in a 40,000 cubic millimeter parcel of air. The air pressure is also constant at sea level here. And so we're starting on our line down here at point number 1, in state number 1, with an air temperature of 60 degrees C and a relative humidity of 10%. And now if we lower the air temperature to 25 degrees Celsius, you can see we move up this line to state number 2, and we can see that the relative humidity has increased to 56%. And if we happen to cool this parcel of air even further, say all the way down to 15 degrees Celsius, you can see that these conditions will arrive at 100% relative humidity, which means that anything at or below the air temperature will have condensation form. And in fact, any water that is contained in the air could rain out of that. This is when you have rain forming in an external macro environment. Now, in real world systems, this behavior is a little more complex because the absolute humidity will actually change as the temperature changes. So we're not stuck perfectly moving along this line. And it's actually something called the specific humidity or mixing ratio that remains constant. But the basic relationship between relative humidity and temperature remains. The statement we want to emphasize is this one in red here, that a reduction in air temperature leads to an increase in relative humidity. Now, one of the reasons relative humidity is referenced in all the environmental specifications is that it's relatively easy to measure. On the other hand, there's no equipment for measuring absolute humidity directly. It's always calculated indirectly using relative humidity, temperature, pressure, etc. So for relative humidity, a capacitive sensor is formed using 2 electrodes with a layer of polymer in between serving as the dielectric. The dielectric constant of this polymer changes as water molecules move into it, thus changing the capacitance of the sensor. You can see that the response of such a device is pretty linear with relative humidity. And these individual sensors are relatively low cost, and you can integrate these into a circuit board within a system, or you can purchase complete electrical modules that convert the capacitance data from an embedded sensor into a conditioned signal over a communications protocol such as I2C. And for the monitoring of electrical systems in the field, You can get battery-powered data loggers that will record both the temperature and relative humidity so that failures in a population of power converters can be correlated with certain environmental conditions. The effect on power modules. So most industrial power modules in the power ranges we're discussing here, say 1200 volt or 1700 volt IGBT modules with multiple switches bigger than 10 amps, are not hermetically sealed. That means they are not gas tight, and that air and the water vapor contained within can move into the module. The air can move through seams in the plastic housing when housing is made from multiple pieces of plastic, or seams around the electrical terminals, or in the holes that were used for filling the silicone gel during module production, or even through the plastic itself. Silicone gel is installed inside a power module to provide electrical insulation between conductors. Now, most people think of silicone as being impervious to water, and certainly silicone can stop the flow of water in its liquid state, as anyone who has caulked a bathtub with silicone sealant knows. However, what is less apparent is that any low molecular weight gas, such as water vapor, will diffuse into silicone gel and move around just as it would in air, albeit at a much slower rate. Now, I wouldn't characterize the water molecules as being trapped in the silicon because they can move from the gel back into the air. But because of this difference in speed, as well as the two mechanisms I'm going to describe on the next slide, once the water molecules have diffused into the silicone, it will take some time to get them out. So once inside the silicone gel, the water molecules do two main things. The water molecule is a dipole, meaning that the side of the molecule with the oxygen atom has a partial negative charge. This charge causes the molecules to be attracted to the electrically charged surface of the chip and the substrate where they can accumulate. The other method of moisture accumulation is not electrical but thermal. So if the chip or the surrounding surfaces are cooled below the dew point for the given conditions, outright condensation can occur. We'll look at how this can occur later in the presentation. Once those water molecules have accumulated on the surface of the chip, whether through electrical or thermal means, the water can cause corrosion. This is of concern at the edges of the chip, where there is a combination of passivation and field plates that have been designed to lower the critical electric field strength and prevent voltage breakdown across the edge of the chip here. This moisture can corrode these field plates or even cause dendrites to grow that can short out the plates. And the end failure is a voltage breakdown from cathode to anode in the case of a diode, or from IGBT collector to emitter, and possibly the gate as well, since there may be a gate runner around the outside of the chip. What I want to point out here is that this is a long-term failure mechanism that can take months or years in the field depending on the level of humidity. So for evaluating the robustness of a module or chip against this failure type, we use accelerated testing. The primary test for checking the robustness of the chip against these long-term corrosion effects is the high voltage, high humidity, high temperature reverse bias, or HV H cubed or H3 TRB test. This is done by placing the power module inside a temperature with a fixed temperature and humidity and putting the semiconductor switch in the reverse blocking state. We place 80% of the device's rated blocking voltage across it, and we measure the reverse leakage current over a period of time. And with any luck, after a certain period of time, typically a target of 1,000 hours, the device still blocks its rated voltage and doesn't show any signs of the corrosion we just described on the last slide. As a side note, in the past, this test was performed with only 80 volts and was known simply as an H3 TRB test. Later on, it was determined that the impact of the voltage on this effect is very high, and the test voltage was increased to that 80%, and the new name of high voltage, or HV, H3 TRB, was used. Now, I want to point out that this is a very stressful test because we're forcing a high temperature and a high humidity to exist simultaneously in an environmental chamber. We just showed earlier that the relative humidity has an inverse relationship with temperature. So normally if we increase the temperature, the relative humidity should decrease. But because we're in this sealed environmental chamber, we're able to constantly hold a very high absolute humidity by feeding water into the chamber via a humidifier, as well as preventing moist air from escaping and expanding because we have this sealed chamber. In real world applications, we'll see that the relative humidity in the microenvironment inside the module will reduce as heat is applied from the chips themselves. So point one back there, we discussed how moisture can cause corrosion over time and eventually lead to chip failure, and that you can see some evidence of that corrosion. But there's another way that condensation or even just water vapor, that is high humidity, can reduce the effectiveness of the voltage blocking structure around the edge of the chip. This diagram here shows the cross section of the edge of a chip, with the center of the chip towards the left and the edge of the chip over here towards the right. And so in the case of an IGBT, the top of this chip is at emitter potential, and the bottom of this chip way down here is at the collector potential. So the chip thickness is determining the blocking voltage of this device when it's in the off state. And normally when we get towards the edge of the chip, we have this termination structure here consisting of field plates, guard rings, and some passivation, which divides the electric field into these nice, evenly distributed regions to prevent the chip from breaking down when it's in its blocking state. But with high amounts of water molecules, either as vapor moving through the silicone gel near the chip edge or as outright condensation on the surface of the chip, this electric field can become disturbed. And if any one area has too high of an electric field strength, breakdown occurs and you'll have arcing there. The reason I'm differentiating between this failure mode and the earlier failure mode with corrosion is because this failure can occur anytime within an application, and oftentimes there's no evidence that left behind. This is why it's really critical to understand the conditions that can cause high humidity to occur, and if there are failures, we need to consider the circumstances under which the failure occurred. So to that end, I just want to briefly list some things to consider if you do have some seemingly unexplained failures of systems, particularly under the following conditions. Since the failures we just described are voltage breakdown failures, that means that you don't necessarily need to be processing current to have such a failure. The chip only needs to be in a blocking state with voltage applied across it. As we'll see, there are periods of time such as the early morning or evening for outdoor inverters where conditions for this condensation are much more prevalent. The causes. So now we discuss what causes high relative humidity to occur within the microenvironments inside and around a power semiconductor module. Obviously, some regions and seasons will have high relative humidity in that larger macro environment and impact the power system if it's unprotected. Transport and storage of equipment in such regions can trap moisture inside equipment. For example, if it's a partially wrapped in plastic and warm, humid air gets inside, and then the moisture condenses into a liquid once the unit is moved to a cooler location. Or consider the process of water molecules diffusing into the silicone gel inside the power module that we described earlier. A power module sitting in a humid environment may have these water molecules move into the silicone gel, and it takes some time for them and perhaps some thermal motivation to move those molecules out of the power module once it gets to a drier location. Air pressure also plays a role in the temperature humidity on a large scale in the macro environment. So usually this is not considered unless you have a highly sealed enclosure that is designed to prevent water or gas ingress. And as we discussed earlier, relative humidity can change with air temperature. So the biggest issue is changes in and around the power semiconductor modules. And that's what we're going to focus on here, the stuff immediately around the power semiconductor module. So the first one is operating point, and operating point refers to the electrical loading of a system, and in turn, the thermal load on the heatsink module and surrounding air. So what we have here is a power semiconductor module mounted to a heatsink, and that is inside an electrical enclosure, and the coolant could be either air or water flowing through or over the heatsink. And in this first state, the system is not operating, and ideally, this coolant is at or above the ambient air temperature inside the cabinet to prevent the dew point problem we were discussing earlier. And when the power module begins switching, it generates losses and heats the heatsink as well as the coolant that is exiting the heatsink. And so after some time, the surrounding air inside the enclosure may warm up, as well as other components, pieces of metal and whatnot in here, due to heat within the converter. Other components maybe as well are heating this air, inductors, capacitors, and whatnot. So the risk of condensation occurs here at the end when there is a sudden change in load. So in the case of a solar inverter, that might be when clouds move over a group of photovoltaic cells. Or in another converter, there might be a fault and the system is running at full power and immediately shuts off, and the coolant system is continuing to run at its full rate, either full liquid flow rate or full airflow. And both the power module and the surrounding air inside the cabinet are still at that elevated temperature, but that heatsink, particularly for high efficiency liquid cooled systems, is going to cool down quite quickly, possibly reducing that heatsink temperature below the dew point for this microenvironment within the enclosure, and that's when you have a risk of condensation. So these next few slides will actually describe what's happening inside this power semiconductor module when we have a change in load like that. And what I'm showing you here is an actual test that Semikron has performed to determine what happens with the relative humidity inside a power semiconductor module. And so in this test setup we have here, we have an IGBT module, and we can apply current pulses to that IGBT module for some minutes here in red. And the environmental chamber is set at a fixed 25 degrees Celsius air temperature and a fixed 85% relative humidity. And we're going to talk about the temperature and relative humidity inside that power semiconductor module. So how do we measure that? Well, inside this test module we have here, we have both a relative humidity sensor and a temperature sensor. And both of these are mounted onto the substrate of this power semiconductor module underneath the silicone gel. This temperature sensor is standard equipment that's soldered inside a production Semikron module along with the chips. And this humidity sensor has just been placed here manually for this test. This is not a standard accessory here. So we start with a starting condition here where the power semiconductor module has been soaking in this environmental chamber without any power, and the water and air molecules have diffused inside the silicone gel. The sensors inside the silicone gel register 25 degrees Celsius and 85% relative humidity, as indicated by this blue dot here. 25 degrees C, 85% relative humidity. This is our starting point, just the blue dot. And by looking at the climatogram here, we can see that the absolute humidity line that we happen to be on is 20 grams per cubic meter. Now we're going to apply an 18 amp pulse of current to this module for some minutes. So the chips begin to heat up because of the conduction losses in the chip. And this heat raises the temperature of the module from 25 degrees C up to 50 degrees C, as shown by this red dot in the diagram where we are now. We can see that the relative humidity drops from 85% down to 50%, as we expected from earlier discussion. But something interesting that happens here is that heat also causes the silicone gel to expand, as you see from these arrows here. And that larger volume of gel allows for more water molecules to become diffused into the silicone gel. And we've actually increased our absolute humidity from 20 grams per cubic meter up to 40 grams per cubic meter, as shown in the diagram here. We're no longer fixed on that 20 grams per cubic meter line. Now, finally, in this third slide here, we've removed the current pulse, okay? And the chips naturally begin to cool down. And one might assume that because we're cooling the module in our 25 degrees C chamber, that the relative humidity would return right back to that original 85%. However, an interesting thing has happened because the silicone gel has expanded and more water molecules have moved into the gel. Due to that slow speed of these water molecules moving through the gel, they actually stay inside the gel as the gel cools and contracts. The absolute humidity that we've returned to is now 24 grams per cubic meter, which is higher than that starting 20 grams per cubic meter that we registered earlier, which means that our relative humidity is also higher than before. And you can see we've started here, we went down here, and when we return, our relative humidity has sort of overshot, and instead of returning at 85, it actually reaches close to 100% relative humidity. And at 100% relative humidity, we know from earlier diagrams that the dew point is the air temperature. And if there's anything just slightly cooler than the air, there's a risk of condensation. Now, power modules are designed so that most of the heat generated by those chips flows down through the substrate, through the base plate, and into the heatsink. So if we're continuing to cool that heatsink, even after the chips have stopped switching, we could potentially cool the chips and substrate faster than the silicone gel can cool, and possibly faster than it takes for the time that for the water molecules to move out of the gel. And so if the temperature of the chip drops below the temperature of the gel, which is at 100% relative humidity, as we just described, the water molecules will condense onto the chip surface, and we have the problems we described before. Lastly, let's discuss some mitigation techniques. So our goal is really to reduce the relative humidity in those microenvironments in and around the module. And if we return to our simplified IEC climatogram here, there's really two courses of action for us here. So if we're starting, for example, at an environment with a 60% relative humidity, this gold dot here, with 25 degrees C and a 15 grams per cubic meter of absolute humidity, we can reduce the relative humidity by increasing the temperature, for example, up to 48 degrees C. And in doing so, we move down along this absolute humidity line to a lower relative humidity, in this case from 60% down to 20%. Or alternatively, if we can remove the water vapor that's present in our system, we can change the absolute humidity, and we can jump from this higher line down to this lower line while maintaining the same 25 degrees C. So in both of these cases, we've gone from 60% down to 20% relative humidity, but we have different amounts of water molecules in the air. In this second case in red here, we've actually dried the air by removing the water molecules. And it's really important to notice here that raising the temperature alone doesn't necessarily dry something out, since the water molecules might still be present even though the relative humidity has dropped. So one of the methods we'll talk about here is cooling control. So in an electrical enclosure with an air-cooled power converter, we can manage the operating point by monitoring the heat sink temperature here, or even better, the temperature inside the module, and controlling our fan speed. And doing so lets us avoid the condition we talked about in the last section, where a power module is operating at a really high load in a humid environment, and you suddenly shut off the system, and the heat sink is continuing to be cooled. With this setup, we can immediately reduce or stop the fan when there is a quick change in load and avoid that relative humidity overshoot we discussed earlier. And if we monitor the outside air temperature, we can also make sure that we're not drawing in very cold air, such that the heat sink itself is not is cooled below the dew point for this condition, where we can risk condensation. Of course, there are other considerations here, such as ensuring that you're not wearing the fan out, as in the case of simple on-off or bang-bang control with like a thermostat. As well as controlling the speed of that control loop, so that you don't overheat the semiconductors because the fan is too slow to respond to a change in speed that you've given to it. Nevertheless, this fan speed control approach is something that many companies have already implemented for purposes of system efficiency or even audible noise. So that may be something that's already available to the system. For liquid cooled systems, the goal is the same, but instead of varying, say, the speed of the coolant pump, there are items like a three-way thermostatic valve here that allows for temperature-driven control of the coolant. And so the idea here is that the coolant, if the coolant flowing through our heatsink, where our power semiconductor module is already cold enough, we don't want to make it even colder and risk getting it below the dew point. So therefore, for a certain set point, the coolant simply bypasses our heat exchanger out here and returns to the heatsink. Then, during normal operation under load, as the coolant heats up because of losses from the heatsink, once it gets above that set point in the thermostatic valve switches over, and the coolant then starts to go through the heat exchanger, where it's heated, where it's cooled, where the coolant is cooled, and then sent back through the heatsink. In very large systems, there is even something called a coolant heater, which is very useful for making sure that the heatsink temperature is never below the ambient air temperature. thereby avoiding reaching that dew point. And additionally, it lets us warm up this heatsink before starting a system, which, as we know, will reduce the relative humidity as shown in this next slide here. So what we have here is a liquid-cooled power module that has been held in a 85% relative humidity environment until the relative humidity down at that chip level has reached 85%. So what I'm showing here is the results of an experiment very similar to what we showed earlier, except we're on a liquid-cooled heatsink. And this condition of having high relative humidity inside the module could be the situation if the power modules were transported through a high humidity environment, like a tropical environment by ship or whatnot, or if the power modules have been sitting unpowered for a long time in an outdoor environment. For example, in a wind turbine power converter that has undergone maintenance for some days and is not under operation. And in these cases, the humidity inside the power module can actually be reduced by applying some coolant warmer than the surrounding environment. So here, what we're showing is we're applying 40 degrees Celsius coolant, and these curves are given for 3 different ambient air temperatures, 35, 25, and 15, all starting at 85% relative humidity. And you can see how the relative humidity inside the module changes with time as you're running this 40 degrees C coolant. So on the left, you can see that the humidity drops quite rapidly since the temperature of the heatsink increases quickly in a liquid-cooled system. However, we know from a few slides ago that this doesn't necessarily mean that the absolute humidity has changed, and there may still be water vapor present within the silicone gel. And so therefore, the coolant should be applied for a longer duration if we really want to drive those water molecules out of the silicone gel prior to starting electrical operation. So based on experience, for example, in the wind industry, we generally recommend running heated coolant for 24 hours if the system is being commissioned for the first time, or if the system has been inoperable for a long period of time. Electric air heaters are used for heating the air inside an electrical cabinet. And these can help reduce the relative humidity after commissioning or long periods of downtime, as we just discussed. And if the water vapor has a pathway out of the cabinet, running these heaters for long enough can lower the absolute humidity and dry the internal air, just as you would in, an oven in your kitchen. But if the outside environment is still humid, you can still be bringing moisture into the system, and your best hope is that by running these heaters, you'll just keep the relative humidity low, even if the absolute humidity is still high. Generally, during system operation, the losses in components, conductors, inductors, capacitors, etc., are high enough to keep the internal components in here above the dew point. But in the event of a low load or standby condition, these heaters can be used. And these heaters are also important in making sure that the electrical components meet their minimum startup temperatures in cold climates. Shown here are 2 800-watt heaters in the bottom of a 1 cubic meter cabinet. So this particular setup is designed to quickly raise the internal ambient. For actually removing the water vapor from mostly sealed cabinets, a dehumidifier is used. And these are industry-specific units that use the same process as commercial dehumidifiers you might use in your basement to condense water vapor into a liquid, but they have some special features such as the ability to run off of 24-volt DC control power, mounting for DIN rails, or integration with a system hygrostat or controller. And these systems don't have tanks to hold the water, but rather a condensate hose that you feed out of the cabinet. And some of you might balk at the cost of a humidifier or a cabinet heater, but these tend to be relatively inexpensive compared to the cost of the system they are trying to protect. And we can show all of these elements working together in a hypothetical liquid or air-cooled cabinet for a larger outdoor system. And larger might be megawatt class solar or energy storage system. Inside and outside air temperature, heat sink temperature, and internal humidity are all fed into a climate control system. And that doesn't have to be really exotic, as there are some commercial standalone controllers available or a simple PLC. Uh, and since these cabinets are both closed, we happen to have some air-to-air heat exchangers on the top of the unit to maintain the internal air temperature within the cabinet. And truthfully, these commercially available heat exchanger units generally integrate all of this climate control stuff in. And since they're effectively industrialized air conditioners, they do a good job of regulating humidity as well. Nevertheless, here they are circulating air within the cabinet while we show a separate heater and dehumidifier at the bottom. And while these cabinets are sealed, they're not hermetically sealed. And we have vents here with a hydrophobic membrane that are used to ensure pressure equalization. And these membranes repel liquid water and dirt, but they allow air to flow through. So they don't necessarily block water vapor. In this air-cooled system on the right, you can see that we've separated the airflow over the heatsink from the internal airflow. And though it's not touched upon in this presentation, one of the biggest issues with air-cooled cabinets is drawing in pollution, dust and debris into the cabinet along with the cooling air. And of course, it also would draw humid air into the system. And this design here keeps the pollution away from the components inside the cabinet, though ideally we would want some filters for the heatsink air as well. In fact, I would encourage all of you to take a look at any modern multi-megawatt class solar inverter, because there's some really innovative designs where manufacturers have taken great pains to separate the airflow for different components. And in doing so, have reduced the chances of the power electronics themselves being subjected to moist air. Now, for smaller systems, let's say outdoor power converters in the 100 or 200 kilowatt range, or maybe even smaller, what we're seeing a lot of manufacturers doing is sealing the box containing the power electronics and then adding a small hydrophobic membrane vent here. So the incoming wires that the customer would connect to are in a separate component, which the installer is responsible for sealing, usually with a gland seal or conduit with maybe some sort of spray sealant or something like that. And the main compartment is sealed, perhaps to IP66 with some sort of gasket around here. Now, again, since these vents here do not keep water vapor out, they still need some mechanism. You still need some mechanism for monitoring the microenvironment inside the cabinet to ensure that the relative humidity is kept low. And for this power range, since most people wouldn't want to pay for a heater or internal fan within here, it's really important then to monitor the operating conditions that we discussed earlier with a low-cost humidity sensor, and perhaps control that fan speed to avoid dropping the heatsink here below that dew point. So with that, actually, I'd like to finish up the presentation here. Once this is finished freezing up on me here, let me hit end and let me go to my last slide so I can thank you all for ending the presentation here. And I think we can then take some questions here. Everything I've just described is described in a lot more detail in AN 1601, shown here. There's a link. This is available for free on our website. It has a little more details for the diagrams and things like that, and discusses these mechanisms in a little more detail. But again, thank you very much for your time. And with that, I think, Emilio, I hand it back to you.
Certainly. Yeah. Thanks for the great presentation, Paul. We did receive some questions that we can discuss. Let me start here. I'll try not to get mixed up. All right. So um, this is a question I'll kind of take a little bit further, but does humidity affect module reliability even in traction inverters? Is it a common failure mode for IGBTs and traction inverters? And I would take that further and say, are traction inverters susceptible to humidity? And also what other markets are susceptible to humidity here?
On a basic level, all in all non-hermetically sealed, which is most of them, power modules can potentially uh, fail due to humidity. I would say any power module is at risk. I mention industrial to differentiate this, but from like a sealed aerospace module or a specialty type power semiconductor module, and to focus on the power range we're talking about. Again, converters in the tens of kilowatts up to the hundreds or megawatts. Traction inverters are essentially constructed in a similar way to the modules I showed, um, albeit with different substrate materials for higher power cycling capability, better ceramics or base plate materials, but all of them are essentially permeable to the humidity. Now, as we alluded to with some of this, part of what we can do as power semiconductor module manufacturers is try to address this on a chip level and make the chips a little bit more robust, um, with better passivation and termination structures around the edge of the devices. But if you have any module that has a silicone gel type sealant, and even other types of sealant that are permeable to low molecular weight gases, there is that risk.
Okay. I'll jump to a different question here because you mentioned it. So you were talking about silicon carbide. Are there any specific tests or requirements based on the die? So silicon versus silicon carbide.
Um, Not necessarily. No, I would say no, because what we're talking about is a packaging, um, packaging and chip level thing. The testing is still the same, right? So silicon carbide power semiconductor modules are also subjected to this same test, um, uh, that silicon modules would be, an HV, H3 TRB test. The chips are smaller and have different termination structures perhaps around the edge, so they might respond differently or better even, to be honest. But we would subject them to the same type of test, whether it's silicon or silicon carbide chips.
Okay, so it's about the packaging and not the chip necessarily.
It is about the chip. The chip design plays a role in its robustness, of course, but we don't test it any differently. We want to hold it to the same standards, because this is intended to represent, the worst case environment.
Right. Okay. So, different topic here. So you showed a relative humidity versus temperature curve at the ground level. Do you know, is this affected by altitude if you go up or down? There's an example here of 5,000 feet, but, basically altitude.
Yes, it does. So this is affected by altitude. Um, Without telling you the exact numbers, I would say, in most cases, it's not so severe that we don't get into calculating it separately, but yes, it is. So, um, uh, you can look at the equations that give the calculate the saturation vapor pressure of water at, or water vapor at, at different altitudes, and these curves would shift a bit, but um, yeah, you would just account for that with the calculations. Um, the One of the other points too is that it's the pressure is really dictated mainly by the environmental conditions outside. So if you have a thunderstorm passing through, that's really going to set the air pressure in the area. I mean, as anybody who's felt their ears pop when a storm is, or a high pressure zone is coming through, that's really what determines all of this. So you can certainly adjust IEC climatograms for different altitudes, or pressures rather.
Okay, makes sense. So for relative humidity, you talked about maximums and things. Is there any minimum required relative humidity for correct operation?
Frankly, from a power module standpoint, I would say no. Um, but unfortunately, the climatograms that are defined here, you can see the minimum happens to be 5%. And that's just the way the IEC has decided to define these environments. I understand that in very select locations on the planet, Death Valley, deserts in the Middle East or Central Africa, you may have 2% or 1% relative humidity. And from a module manufacturer standpoint, we don't we don't require that there's some minimum amount of water in the air. So in theory, I would say you could have 0% relative humidity if it were possible to do that. But it just so happens that the IEC standard, this 60721, starts at 5%. That's a choice they've made, I think, because they felt that was what was out in the world.
Okay. Um, and here's one I think you would be good to answer. So the humidity condition causing overvoltage, could it reveal itself as a black mark on the transistor or diodes? So typical in those
Yeah.
types.
So we're talking about this failure mode here, where it's not corroding, but your electric field strength has been exceeded in an area. If
Right.
you exceed the electric field strength, that means the chip is not able to block the voltage in that area. So, if it's a 1200 volt device, and the blocking voltage strength has been reduced to 800 volts or whatnot here, if you have a voltage higher than that, you would have a over voltage condition, and you would have a short circuit there. So um, that starts out as a little burn mark there, okay, and a short. And if you don't limit the energy, if there's not a fuse in the system, or it's fed from the DC link, it's possible that once that short has started, that you could have more burning, and then you could burn up the whole chip. But if you're able to catch it early enough, you would see burn marks in the area of the edge passivation or guard rings out here, or the edge of the chip. It all depends on where the moisture has accumulated, where the condensation has happened. It could be by the edge of the chip, it could be in these guard rings, um, but that's the high risk area, is at the edge of the chip. It's not to
Okay.
say it can never happen in the center, but the high risk areas in the edge, and you would see a burn mark in these areas.
Which falls to another question I see, asking if there's anything that can be done at the chip level for improving against humidity.
Absolutely. So a lot of it involves improving this passivation structure here. So there's a material, polyimide, or other types of passivation. Okay, older chips have glass passivation, but there's methods you can do to make this more robust against condensation that occurs here. Um, and that's where lot of a lot of the work is being done. So uh, it's tough because chips are getting smaller, right? Every chip generation gets smaller, which means we have to block the same amount of voltage in a smaller area. So a lot of voltage stress is occurring over a smaller area here. So chip designers have to become more clever with how they design these guard rings or field plates to divide up that field strength, and also have to make it robust so that uh, if the water does accumulate, it either doesn't cause corrosion or doesn't disrupt the behavior of those. So absolutely, it's primarily a chip level thing. Primarily starts on a chip level, and then anything that the module manufacturer does can, also impact that. So
Okay.
it starts at the chip and we work our way out. Yeah.
Okay. So some environment with high humidity also presents a significant level of salinity, such as areas close to the shore. Is there any
hmm
differences on the analysis of a situation with salinity plus humidity for the ones with only humidity?
Um, Everything we're discussing here is just humidity related, but um, I guess salinity. I'm not a chemist, so can't speak how sodium ions or anything are distributed within the vapor. But the mechanism I talk about earlier here, where we have what I say low molecular weight molecules moving through here, uh, could be any gas. So for salinity, high salt environments, we usually worry about corrosion on bus bars and conductors and things like that. I can't point to evidence of salinity or salts inside the module, but it should be, in theory, it should be similar to another problem that we have that's not addressed in this thing, which is corrosive environments with stuff like sulfur. So sulfur molecules in maybe wastewater treatment plants or paper pulp processing or things like that. Uh, what the issue there is that in addition to water, you have sulfur molecules coming in here as well, and those interact with the water and form very corrosive acids that corrode the copper and other conductors within here. So I guess again, I'm not a chemist, but it's certainly possible. I would think that you could have salt solutions or things forming as well. So other molecules potentially make the situation worse. But I would say the primary breakdown, because it's a shorter term and can happen at any time, is this disruption of electrical field and condensation issue on the chip. Because the corrosion, whether it's due to salt, sulfur, or anything else, is a longer term a problem. But this can occur on quote unquote new systems, or the first time you start up, if there's enough humidity in the system.
Okay. I'll give you one last question before I call it quits. So, um, the temperature, let's see, how do I phrase this? How the temperature affecting difference affecting the pillow. So how could we make sure that that we're able to meet these harsh environments? So what kind of tests, whether it's FAT or SAT, could be performed to make sure that they're in compliance?
One is making sure that you're getting modules from a power semiconductor manufacturer that have passed so-called HV, H3 TRB. So some of the testing is done by the module manufacturer. Some of our customers will repeat this testing on their system. Ideally, if it's feasible, you know, the what we'd like to see is a finished system or cabinet. So let me go to a picture. A system like this. Ideally, we would like to see this finished unit put into an environment like defined by the IEC standard, and then run and tested. Now, this, of course, this isn't always practical. You may not be able to fit this whole unit inside a chamber, but if you can, that's obviously the ideal, because then what you're testing is your system, and you're making sure that your sealant, your enclosure is doing its role in protecting the power module from the outside environment and controlling the inside environment so that you don't have high humidity conditions. Short of that, if it's an outdoor thing, I would love to see a pilot site, right, where you can have, say, a solar inverter running for some time in an outdoor environment and operating under these different conditions. Like I said earlier, one of the risk points is running at full load and then stopping quite suddenly while you're still cooling the system aggressively. So you would want to check for that operation. And if you can install it in an outdoor humid location, great. If you can install it in a climate chamber with a fixed 85% relative humidity, that's great as well. But I would say most of the testing is on the power semiconductor module manufacturer to make the module robust, and then after that, the equipment manufacturer needs to test operating conditions that would affect the unit. Like I said, the cooling the heatsink too much, cutting out the power, controlling the fan speed, things like that.
Okay. I think that's. I'll leave it to that. I'll stop asking you tricky questions, and we'll call it a day.
We will
Paul, thank
answer
you
the
once again.
tricky questions by email. Yeah.
We'll answer the rest of the tricky questions by email. So, to the audience, thank you for joining the webinar today. Thank you for participating and asking all these tricky questions. I hope you enjoyed it, and I hope that you could take away some useful information. Please join us for future webinars. Have a great day. Bye-bye.